Let's go with a quick recap first. Electrolysis is the breakdown of an ionic compound with the help of electricity. That's what electrolysis is. Electrolysis table is a good way of putting all the resulting information number from electrolysis process itself into just one page. So right now we are only doing molten compounds, which means every salt I'm going to name over here as an electrolyte. Electrolyte is a liquid which can conduct electricity. It automatically means it's present in a liquid state. We're going to tell the products at cathode. Cathode is negatively charged, so positively charged ions is going to come over here, and of course they will get reduced. We're going to explain the product at anode. Anode is itself positively charged, and oxidation is going to happen over here. All right. Reduction means the element that is going to come, the ions that are going to come over here are going to gain electrons. As you can see, electrons are being added to it. Oxidation means that the ions that are going to come over here are going to lose electrons. And as you can see over here on the right hand side equation, that this ion is losing some electrons. Change the electrolyte stays the same in molten compounds. We actually use the whole melted portion to convert it into its constituent elements. Take a look. Sodium chloride is made up of sodium. So sodium is something that we get as a product at cathode. It is also made up of chlorine. Chlorine gas is something that forms as a product at anode. So we simply get our constituent elements at two different electrodes. Now, so far was the concept. Let's talk about the quick tip. Even if you don't remember the concept or anything in exams, how are you going to get your answers right and correct? The tip is pretty simple. Whether you talk about the name or you talk about the formula, the something that is written left of it goes to the cathode. Something that is written to the right of it always goes to anode. The metals usually tend to form at cathode. The nonmetals usually tend to form their diatomic molecules at anode. This is always used up. That's about it. It's as simple as that. Even if I write the name of the salt, and the name of the salt in this case is sodium chloride, it's pretty simple. Sodium is going to be a product at anode, cathode, and chloride is going to be a product at anode. As simple as that. So whether we talk about the name or we talk about the formula, something on the left goes to the cathode, something on the right goes to the anode, and metals and nonmetals respectively form at cathode and anode. I hope that makes sense to you both, right?
Yes, sir.
Okay, so let's practice further compounds. There are some more examples. Magnesium and bromine. How do we come up with the ions? Magnesium has a +2 charge, bromide has a -1 charge in this case. So magnesium has a +2 charge, adding 2 electrons would neutralize it. Bromide ions have a negative charge. If we take out electrons, it would become neutral. But since they form diatomic molecules, so we need to make sure that we take two ions and extract from them the exact same number of electrons, which can make them neutral. That's how we do it. So moving on, Ki, potassium is also a good example. So we get potassium at cathode, iodine at anode. Both the charges are +1 and -1. So it's pretty easy to solve. Next up is strontium chloride. So Sr or strontium goes to cathode and chlorine goes to anode. With similar set of equations, it should be easy. Now, I am not going to scroll much, just a little. Now, you do understand that you have molten lead bromide as the next example. And as you can already see, the products at cathode and anode are lead and bromine. Why don't you go ahead and try writing their equation? If you'd like, you can annotate it on my screen. If you'd like to do it on a piece of paper and send me a picture, it's entirely up to you. If you're going to annotate on my screen, One of you can take the right hand side, one of you can take the left hand side. You can always annotate, but make sure you use different colors. Go ahead. Try doing it. It's not a problem. You may make mistakes in your first attempts. Don't be shy about making mistakes. Actually, making mistakes is going to get you confident with your work slowly, of course, taking you towards a mistake-free work.
Sir, can you solve it on the left?
Yeah, sure. Go ahead. It's fine.
Okay. We will get this at the cathode.
Good. Wes, would you be practicing it now, or will you need some more time and understanding to practice it? Start practicing a little later.
I need practicing and more understanding to be confident enough to solve it on myself.
I can hardly hear you. It's like you're too far away from the mic.
Sir, I still need more practice and more understanding to be confident enough to write,
Okay.
solve myself.
Sure, sure, no problem. Then keep on paying attention to what Ariba is doing, what I'm doing. Slowly, you'll get a grasp of what we are doing. Since, of course, it requires a little bit of prerequisite. You're right about that.
Sir, we will get this at the anode.
Good, good. Now, since this is a table and this already consists of a bromine equation, so it should be easy. But apart from that, even if you haven't cheated, that's right, good. So two bromide ions give us bromine liquid, and they actually give away two electrons. All right. So moving on. Next, copper to chloride. Let's start with copper first.
We will get this at the cathode.
Good. Since chlorine's equation is something that we have repeated a couple of times and it's right here on the screen, so you don't need to write it. In fact, I'm going to give you a new compound. So I don't know whether you have tried it previously or not. Why don't you go ahead and try magnesium nitride, Mg3N2?
Yes, sir, I've done that. We did it in the last class.
Okay, if you're done with this one, let's try aluminum iodide, ALI3.
Okay, sir. We would get this at the cathode.
Good. Since iodine's equation is already a part on the screen, so let's skip it. Instead, let's do something which is not here on the screen. So I would like you to solve something like this. CAS, calcium sulfide. Since neither calcium nor sulfur is a part of screen right now, so it should be totally new to you.
We get this at the cathode.
Okay. This time you need to fill in us with anode's information as well. Go ahead. What about anode? While Ariba is at it, Aves, can you let me know which group does calcium belong to in periodic table? Open up the periodic table in the hard copy of the book from the end of the book or the mid of the book. That's entirely up to you. Don't solve this question blindly. Take help from the periodic table, please.
It's the second group.
Good. Group 2.
Alkyne, I think. Yeah, alkyne.
Yes, it's group 2. That's fine. That's the correct answer.
We will get this at the anode.
Okay. What if I tell you that both the equations are incorrect? And they are incorrect due to the reason that the charges on the ions are not correct. Just to give you a hint, I just asked Aves a question that which group does calcium belong to? He tells me that calcium belongs to group 2. If calcium belongs to group 2, the charge on calcium would be, what do you think?
Oh, positive 2.
So if the charge on calcium is positive 2, that definitely means the charge on sulfide ion would be
Negative 2.
right, which actually changes both the equations. So go ahead, make the appropriate changes. Let's see the corrections.
They can say, won't it cancel out?
Sorry?
Won't the ions cancel out because it's positive 2?
Yeah, they
It's
do cancel
negative.
out.
Won't
They
it?
do cancel out their charges, but that doesn't mean the charges never existed. When we're going to separate them, they'll separate it with their own charges.
Would it become CA negative and S positive?
C would be positive too.
Say I don't get it.
Okay, let me clarify this. This is the part where this gets difficult. Otherwise, electrolysis for molten solutions is something that is pretty easy for most of the students. Since they cross multiply these numbers and they always get to the right ones. For example, we had a 3 over here. If you take this 3 over here, it would become plus 3, and you have used this 3. And we have no numbers over here, so it's understood this was 1. If you take this 1, iodine would be negative 1, and the same negative 1 has been used over here or here by the student, the one who compiled these notes. Now, in case of having no numbers over here, assuming that this is 1 and this is 1 as well is not a good idea. Then we ask our students to take help from the periodic table. Look the elements up, what group they are at. Now, if you look it up, you'll find that calcium belongs to group 2 and sulfur belongs to group 6. Now, this clearly tells us that our assumptions of 1 and 1 were wrong. So, what do we understand from this? If calcium is from group 2, it is going to lose 2 electrons to form this compound, so plus 2. And that's how its octet would be complete. And sulfur will actually gain those 2 electrons, complete its octet to form this ionic compound. Now, we understand that we cancel these ions and we don't write any numbers below, but when it is reversed, they will be reversed with the same charges that it started off with, even before cancellation. So calcium would be 2 plus, and we'll have to add 2 electrons to it to convert it into calcium. Sulfide would be 2 negative, and it would be converted into sulfur after losing those 2 electrons. And that's how both equations are complete. Make sense?
Yes, sir.
Okay. Now we are done with many equations. Before we can move on to aqueous solutions, there is one more perspective of it that we need to finalize. And that perspective is the observations we see. Of course, whatever we are writing over here in terms of education is background chemistry. This is something happening in the background, in imagination. Something happening is so small that we can't even see the electrons going from one element to another. Then what do we see in front of ourselves? We usually see that these metals are produced as solids, which get deposited at the cathode. So if a metal is getting deposited at cathode, it must be able to show its colors. So what happens? And you already know, I don't think I need to tell you this since we are done with the periodic table portion of the chapter, that be this metal, be this metal, this metal, this metal, or this metal, all the metals have the same color in the word except for two. What is that color? What colors do all metals possess? This is from periodic table portion, periodic table chapter, periodic table portion, the metal and non-metals
Um,
difference table. I guess that is page number 57 on the book.
silver?
Silver, great. We either call it silver or we write it as silver gray. All the metals in the world have a silver gray color, except two metals. Which two? The first one is gold, the second one is copper. So what's the color of gold?
Golden.
Pretty easy. Gold, golden color. What's the color of copper?
Red brown.
Red brown. All right, great. So in this last experiment at the bottom, we get to see copper forming at cathode. This means there would be some red brown metal depositing on the top of the electrode. However, in all these cases, a silver gray metal will be deposited at cathode. Make sense?
Yes, sir.
Good. Now this was pretty easy. Metals are usually easy. You don't have to remember too many colors. It actually is the non-metals where it gets difficult. Now we can see mostly halogen over here. You can see chlorine, bromine, iodine. Now can you tell me the colors individually? Chlorine is a gas. What is the color of this gas? Again, this is from the same periodic table chapter.
Yes. Chlorine has pale green color.
Good. What about bromine? Bromine is a liquid at room temperature, and the color of bromine is
It is also red brown.
great. Finally, iodine. Iodine is a solid at room temperature, and the color of solid iodine is
It is gray solid with purple vapors.
that's good. So obviously, if you can remember the observations, this is actually the easier part of the electrolysis. Why? Because you can simply memorize it, and from your memory, you can answer every kind of questions with it. So I hope you will be able to cater the observatory parts of electrolysis. All right.
Yes, sir.
So what have we prepared? Let me actually summarize this up for you. Okay, this table, since this table tells you a lot about what we have prepared, so let's make sure that we learn all the possible kinds of answers to the questions. Now, there are many kinds of questions, so let's go through the list. First of all, they may ask you the products that form at a specific electrode or electrodes. The name of the products are written over here in the table. So every time they come up with an example, you'd know what to write. Make sense?
Yes, sir.
Secondly, they may ask you to write half equations of any of the electrodes. If they ask you to write the half equation of cathode, you have these equations over here. If they ask you to write the half equation at anode, you may write this equation over here as per the given example, whatever example that is. So the second thing that is usually and most commonly asked in past papers are half equations. We've already practiced the half equations. Number three, type of reaction occurring. Now, from type of reaction, they actually try to mean whether there is oxidation occurring on that specific electrode or reduction. Now, this is mentioned in the very top part of the table. And since this is fixed for every electrode, it shouldn't be a problem. Oxidation always occurs at cathode. Oh, my bad. Oxidation always occurs at anode. Reduction always occurs at cathode in case of electrolysis. So I think this should be easy. We should remember the type of reaction for a specific electrode since this does not change from example to example. Equations were changing from example to example, but type of reactions does not change. So it should be very easy.
Yes.
And finally, the fourth and last part they usually ask from students is observations, which we just discussed. A solid is depositing on top of an electrolyte, electrode, or a gas is bubbling out of the system, or a liquid is flowing around with the rest of the molten material, or a solid is settling down at the bottom of the container. Those all depends upon the observation we are getting. And we've just practiced the observations. In observations, you should know the three simple things about the colors of metals. All metals are silver gray in color, except for gold, which is a golden color, except for copper, which is a red brown color. As far as the colors of non-metals are concerned, yeah, you need to remember them separately. Since there are 10 to 12 different non-metals, you need to remember all of them separately. What's the color of fluorine gas, bromine, uh, iodine as liquids and solids respectively, or for nitrogen or for oxygen, stuff like that. What's the color of nitrogen gas? Let's ask it from OS. The color of nitrogen gas. Do you remember that? Remember, it's present as a part of air. So this should be easy to answer. Right, can you hear me?
Uh, yes, I can hear you now, sir. I got confused if you were referring to, uh,
I'm referring
can you
to
repeat the question?
I'm referring to nitrogen gas. I actually am trying to take out the product from here. The product is nitrogen. It is present as a gas, and it is the biggest part of our air around us. My question to you was, what is the color of this nitrogen gas?
Sir, it's invisible, colorless.
Colorless. The term that we use is colorless, right? It's colorless. Okay. So yeah, the gases like these, nitrogen or oxygen, are colorless gases. So now you know about all the kind of questions you can face from the molten system. So next question, would you like to practice it more, or is it good enough? Ariba, this question is for you, beta.
Oh, sorry, sir. Yes, it's fine, sir. We can move forward.
Okay, then if we're good with this, let's move on to aqua solutions, electrolysis of aqua solutions.